In this video, I will draw a beautiful picture for you. I will draw a happy tree for you. Let this be our ground. A tree stands on its roots. So we will draw its roots first. The stronger the roots are, the stronger the tree will be. This is a big tree, and the branches are result of its roots, and number of branches and its strengthness all depends on its roots. There is a happy little flower. Let me draw a bigger one. There is a happy little flower. We have green beautiful leaves, and all are because of its roots only. Let us have another happy little flower. And all are because of its roots. So in the end, that is the root which decides everything. If this is a tree of group theory, then its roots are the axioms of the group. Its closure and this is associativity. This is identity, and inverses. And these are the building blocks of group theory, and these happy little flowers and beautiful green leaves all depends on these roots, and these are theorems. Results. This is a happy little theorem. Happy little theorem. Lemmas and propositions. And all these beautiful things all depends on the axioms of the groups, and these are the building blocks of the group theory, and they decide what its tree will be, how its tree branches, how its leaves, how its flower will be. From all these beautiful theorems, propositions, results, in this video we will see three elementary properties, elementary theorems. Let me erase it. At first we have a happy little theorem. And this is on uniqueness of identity. See, by the axioms of the group, in any group we have one identity. But what about two identities? Can there be two identities in a group, three identities in a group? And this theorem says no. Uniqueness of identity. And this theorem says in a group G star there exists only one identity. Next we will prove this theorem. Proof of the uniqueness theorem in mathematics applies this procedure. Assume there is two things of that item, then in the end show that those two things are not different, they are same. If that is the case, then the uniqueness is proved. We will also do the same procedure. Let us assume E and E dash be two identities of group G star. See, if E and E dash are two identities, then E star E dash, I will take E as identity and E dash one element of G, and what identity does? E star E dash is E dash, as this is identity. Now I will treat E dash as another identity, and this is E, this one will be what? This is, because I am treating E dash as identity, and identity times identities when operated with any element of the group G, you will get that element. So by these two lines we have, that implies E dash is same as, and this happy little theorem is proved, and we are happy. So in any group we have how many identities? We have only one identity. Let me erase this. We have another theorem now. This is also a happy little theorem on inverses, and theorem says there can't be two inverses. Uniqueness of inverses. This theorem says there can be two inverses of one element of a group. And statement says in a group G star, for each element A of the set G, there exists only one element B in the set G, such that A star B equals to B star A equals to E, which is identity, is the identity of G. In fourth axiom we have every element of a group has inverse, but this theorem says there can't be two inverses or three inverses for one element. One element can have only one inverse, and we will prove this theorem. And proof follows the previous procedure. We will assume two inverses of A. Suppose B and B dash are inverses of A, then what we have? We have S. When operated with operation star with B, it will give the identity. And let us operate this element with the inverse B dash. B dash, I will use another color. B dash, when operated with the element A star B, operation star. In the right side also we will operate E with B dash, and this is B dash star E, and by associativity I can write this one as B dash star A star B, and this is V dash, because E is the identity and B dash one element of the group G, and we have used associativity here. By associativity, and this says this is one inverse of A, and now we have this is identity, and this is star B, and right side we have B dash. Let me use the color. B dash up, B dash, and this is B. And right side we have, and this happy little theorem is proved, and we are happy. Let me erase this. Please pause the video to note the theorems. I will erase now. So in a group we can have only one identity, and for every element of a group we have only one inverse. Now we will see another theorem, that is, this is also we are happy theorem, and this theorem on cancellation. Right, when we are dealing with algebra, note, when we have one equation 2x equals to 2y, and we used to cancel 2 and write x equals to y. We are all familiar with cancellation. We used to cancel things from each side of the equation. But is it true for every cases? Let us see. Suppose we have 0 times one is this x, and this is multiplication. Suppose 0 times 2 is 0, and 0 times 3 also 0. So left side and right side are equal, but we can't cancel 0 because 2 not equals to 3. So we can't always cancel equal things from each side if they are multiplied. And same holds for also in matrices. Suppose we have one matrix 1 1 0 0, and they are multiplied with another matrix 3 1 0 0, which is what? This is 3 1, this is 4 0 0 0, and suppose I am, this is 1 1 0 0, and I am using another matrix. Let it be 4 0 0 0. Then also I have 4 0 and 0 0. This one is same as this one, but we can't cancel this one because this is not equal to this one. So cancellation always not hold. But in a group we have cancellation. We'll see in this theorem. Let me erase this one. We have two cancellation. One is left cancellation, another is right cancellation. In a group G star, we have left cancellation and right cancellation. So what is left cancellation? What is left cancellation? Suppose for A, B, C, three elements of G, we have AB equals to AC, then we can cancel A from, and this is operated with operation star. We can cancel from both sides, A from both sides. And what is right cancellation? Right cancellation, same thing, we can cancel from right side. For ABC, if we have a B star A is same as star A, then I can cancel A from both right sides and B equals to C. And this cancellation property holds in any group. We'll prove this. So, let us prove many cancel. Let us first prove left cancellation. Suppose we have A star B equals to A star C. Let us operate this element with the inverse of A from left side of the both of the sides, left hand side and right hand side. I will apply A. That implies A dash star A star B equals to A dash star A star C. I have taken A dash is the inverse. I can now use the inverse because inverses are unique. The inverse of A. I have taken A dash as the inverse of A, and it is the same as. Now I can use associativity. B. Associativity. By using associativity, now what we have, this one is identity E. Let me use another color for E. This is E and this is B, same as E star C, and we have taken E as the identity, is the identity of G of group G star. Now we have in left hand side we have B, and in right hand side we have C, and we have cancelled A from both sides. And this is possible because A have inverse and we have associativity, so we can cancel A from both sides, and left cancellation is proved. We are happy. Similarly, in the same procedure, we can prove the right cancellation. Similarly, we can prove the right cancellation. You have to just apply a dash on right side and use the associativity. You will get the equals to C. So pause this video to note it down. Don't please students, don't hesitate to comment in the comment section the doubts, and I will try my best to clear them. So, thank you.